Right. So I have used quite a few examples from Hadley's because I think, realistically speaking, function factories are relatively straightforward in a way. In terms of concept, it's the application of them that's quite difficult, and that's where I think people have problems with. So let's just start it off then. So what are function factories? Is what we're going to look at. And how you use those to basically build manufactured factories, and then how we use those manufactured functions, and how those things are implemented, and some issues that you can come across, such as with promises and needing to force vectors. There's also a package which John has developed, which is just called Factory, that helps some issues. I'm not entirely particularly okay with it, but he put in the original presentation, so I left it in there because it looks like something that people might want to investigate. And then at the end, we're just going to look at a few examples of how to make use of function factories. So what is a function factory? So last week we did functionals, which is, so basically you put into a vector into functional, and you put a function into it and you get a vector out. So if you put data frame in, you should get data frame out after like mapping across a list or something like that. So you can go across several functions, map across it, and you get back the data out of it. Whereas with function factory, it's instead you're using it to build more functions. So the ubiquitous example of this, before we go on to that, so there's three key concepts that Hadley mentions in the book. So the first one is that, as we already know, functions are bound in the same way that we bind things to an object with the general assignment operator, as we've got at the top here. And then two other factors are important, which is that we have enclosed environments, which is that functions capture the environment in which they're created. So they basically take the environment when you're creating an environment. When you're creating a function, any function created within a function factory will steal that environment in which it was made, essentially. And then another key aspect is fresh start. So we already know that when we run a function, it should start fresh each time. So it should basically clear the environment. So if we rerun a function, it should give us a fresh analysis, as opposed to basically memorizing the data that came before. So here's the ubiquitous example of a function factory, which I think is kind of boring, but essentially, it's very basic kind of algebra, isn't it? Which is you've got an exponential. So what you do is you put in a number and you increase it by the exponent that we've selected. So in the case of a square, what we're doing is we're multiplying something by the power of 2, and if we're going to cube it, we multiply it by itself 3 times. So if we have, so in this particular example, if you put 8 into square, you've got 8 times 8, that's 20, that's 64. So what we have here is we have the function factory, and in it is what we put into it is an exponent, and what that exponent essentially does is it takes x and it increases it by exponent or exponential. So basically the exponential is increased. And then the manufactured environment is basically whatever we've put into that. So what we say is we've got power 1 and we've assigned that 2. That means that it's going to raise a number by the power of itself twice. And with cubed, it just does that 3 times. So it all depends on what we're assigning to the 3 value, to this value here for the manufactured environment. But within the function factory, it doesn't actually output a number itself. So to go back to this idea, the reason why it's quite important to understand the environments in which function works is because, well, we'll get into it later, but functions can maintain a state. So when we look at the enclosing environment, Sorry, 1 second. I need to get my notes up. So when we're looking at the environment, just printing the function shows us that it doesn't show us anything particularly interesting. So these manufactured functions that were created from our function factory just show us basically the same body, but with different environments. And these environments basically being inherited from the enclosing environment from which they were created, which would be from what we called up here power 1. So when we call power 1, that environment was captured into square 1 or into cubed 1. And this is basically how it works. So in the book, it shows this, and they cut off the bottom half of the screen and just show it as going along. I actually think that makes it more complicated to understand. So essentially what we've got is the exp function, which is assigned to power 1. And then we've then reassigned that to cube 1 and square 1, those values. And what that does is it takes, those have their own execution environments in which we've assigned either the number 2 or the number 3. So the exponent will be raised by those powers. So where we store our values is in the execution environments of the manufactured functions, if that makes sense. So this creates a few issues later on, which is that because functions, because of lazy evaluation, function factories, when they're taking a number, or when you've got a number in the manufactured value, it can change what we see at the end. So we see here that we're putting x into our function factory, and it's 2, and then we create square b, which is just redoing the square value. So if we put 2 into that, we expect to get 4 out of it, not 8. But what happens is because the function is evaluated lazily, it takes whatever the most updated value of x is. So in that case, that's 3. So instead of going instead of squaring, we're cubing the number instead. So in order to avoid this, what we have to do is to force the evaluation. So there's a function called force in base R, and essentially what that is we just put this wrap round exponent in force, and it stops it from reevaluating the number back here. So when we go down to the bottom of the screen here, we've put x to number 2 and x to the power of 2, and so that has now taken what we've assigned to x value. So when we reassign it, it doesn't change the function that we've created. It's been forced to be 2 rather than being allowed to vary to whatever the changes in the vector x. And that means that we'll end up with the correct value in the end. So John built a package called Factory, which they appear to still be working on. And essentially what that does is it allows you to basically create a function like we did before, apart from you wouldn't have to add force in, it will automatically do it. And it does a few other things as well, which I'm not particularly familiar with, but as you can see, once you've created it and you actually print out the function, it just prints out a very simple function that stores it as x to the power of 2 instead of actually writing out the equation as we have it up here. Not really sure exactly why that's so good, but I'm sure someone else will know or understand because I haven't had time to research it, unfortunately. So does anyone know? Emily?
I was going to say, I've never used this before and I had never seen it before, but I imagine this is more useful for people who are doing a lot of complex math and sort of like building out their own equations within R, because I can't I'm having a hard time visualizing when I would do this outside of a math context.
I think that not many people use function factories in general anyway. They're not very common, as Hadley Wickham said at the beginning of the book, they're not commonly used, but they are really useful for statistics. And the examples he uses at the end of the chapter are for like maximum likelihood estimations and for like lambda, finding the best lambda, stuff like that. And it's kind of just a way of, I suppose, systematically working through values, but you can apply it graphically as well, which is how it tends to be used, like in things like scale. Was it scale R? But other than that, they're not very common in the overall. But I think they probably could be really, really useful as you get further into like your data science career, or but then even then, like John says, he doesn't use them that often, so I'm not really sure how often these are. These do become particularly useful even for those who do a lot of data science. But maybe that's just because we're not so familiar with them. Maybe it's because as a mental model, a function factory is quite a difficult thing to comprehend in comparison to just building a normal function. And it's just that one step further in the metacognition, I suppose, isn't it? So why to use them? Most important thing is stateful functions, which we were kind of alluding to before, which is that they allow, function factories allow us to maintain state across time, well, I've written it down there. Of course, each time you call it. So typically speaking, that's when we don't want a fresh restart. That's when we want something to remember what has gone before. So the manufactured, so what this basically means is that that we can then work our way through a list of values which we need to create, but without knowing what those values are in the first place, which is why it's useful for algebraic kind of action. And what makes this possible is the fact that they have their own enclosing environments, and that the environments and the enclosing environment is created from the execution environment of the function factory. So that just means it has its own space. So in this example, typically speaking, what they use is a coin toss example, but in this particular example, which I got from John, you got a hotter, colder example. So what? Oh, I see. Sorry, I've missed out something from the slide. There's a super assignment operator, which is what allows us to do this kind of stateful functions. So if you see down here, every time we're making guesses to what number out of 1 in 100 is the number that we're trying to guess, it remembers whether we've remembered it or not. And then it could, and basically, as we guess, we're guessing 50, we go down to 25, we're getting colder, and then warmer and warmer. And it just kind of works. It remembers where we are compared to where we were. So what that essentially means is that as we change our number, we should get warmer or colder, as opposed to getting, as opposed to being back to where we were. We should be limiting down our options. And that, if you think about coin tosses or remembering those things, that it's quite useful to remember how many we've got right in a row or something like that. So that also then leads to a bit of a problem, which is that we collect up quite a lot of data, and because function factories, manufactured environments hold their execution environment, it basically means that they hold on to large amounts of data, which means that we also need to specifically unbind them, because otherwise, if we don't, we might end up overloading our memory, or we won't be able to run other things on the computer. So essentially, you just want to make sure that you've got the RM function applied within your own function. So another example where we use these are for things like binwidth. So the binwidth can take a specified number, but this isn't always the best thing to do, particularly when we want to vary it across a population. And Hadley Wickham uses this example here, where we have this standard deviation of 1, 5, and 15, and create the R normal values. And what you do is you end up, when you specify a binwidth of 2, we end up with these very skewed looking graphs, which aren't very representative of the population, even though we've got the same number of observations in each graph. So what we can do is we create one we call binwidth 1, which takes the maximum and minimum values and then basically divides that by the values that we've got. And what that essentially means is that we then end up with a much better distribution that's more representative of our data. So yes, the binwidth is different, but it's actually a better comparison. And that's because we've basically created this function here from our function factory. So another example where it's used is on the scale packages, and scale packages is all it's essentially doing is just taking in values and then just spitting out a reformatted version according to particular rules within the function. And as you mentioned before, we can move further down into the into things that are a bit more numeric. So what we have here is another function factory, and essentially what we do is we're throwing in our formulas, and then we're getting all our bitted values, so that we can see we can bootstrap a linear regressions and find which one's best, essentially. And in this particular example, you can see here that we've actually thrown away the models at the end because they create really large data banks. So you don't want that if you just want to boot through and see if you can minimize the values. So that's really it. It's quite a short chapter in a way. It doesn't, in my opinion, it doesn't actually really, it's telling us about a method that is quite, in some respects, quite complicated, and in other respects, it's actually quite straightforward. It's really mostly about the application where it becomes quite tricky. And he does go further into it to look at things like Cox transformations and maximum likelihood, but they're really just applications of the same theory. So did anyone go any further with it, or do the questions, or have any use for the function factories?
I thought the maximum likelihood example was very interesting because I have done that many, many times and never knew what a function factory was until yesterday. So thought it was interesting.
Do you feel like knowing what a function factory is now will change maybe the way you approach it, like the same thing in the future?
Potentially. It is nice to not have to compute all those sufficient statistics or data summaries every single time, but it seems not straightforward how you would include more arguments, I guess. Most of these examples only had one argument in each layer.
Oh, that's something they mentioned, which is that as you get more complicated, you should use R6 instead. I can't remember why he mentioned that. Sorry, I'm just trying to find the instance where I saw that.
I think he said that when you use the super assignment, like the double arrow dash, And I was gonna say something about that. If you're building a package, you can't have that in your package because CRAN doesn't like it. Because
Mm.
then they say your package will be modifying the user's environment, because then that's what it does. It modifies the parent environment. So it's a dangerous thing, because then imagine you create this amazing package, and then the user had this X variable, which it took the person 2 hours to compute whatever is in that variable. But then inside this function of your package, you override X by a true or false value. So CRAN sees it as a potential thing that like it's undesirable to have in a package. So, and then Hadley says that you don't want to rely on that too much, because it's the same thing. Like you don't know what's gonna happen with that variable in the global environment. And R6, I watched the video for another cohort one of these days because I was bored. So I said, let's see what they're doing. And then it was the R6 video. And everyone says that that's the closest you get to object-oriented programming, like in R, in comparison to other languages like Java or C++, in which you have a class, but not a class as you say, this object, class, data frame, or class numeric. But it's a class in which you have attributes, and then it has inside there's functions, and which at the end those classes, and we'll see this in chapter 14, it's a list. Those classes are a list because then you use the dollar to call things. But then it has like a memory. You create an instance of the object, and then you keep modifying it, but then it refers to the same place in memory. So when we did chapter 3, was it? We did about the copy and modify, or copy and then makes another copy. The R6 object makes a modification in place. I don't know what's the right term. Well, it modifies in place, so it doesn't make any unnecessary copies of your objects. And I think that's what he says, like, if you're trying to do this super assignment thing with function factories, you should be looking at R6, because then that's like the way you should want to approach this kind of thing. And you will see that in chapter 14. It's interesting. I had a look at.
So
Very
basically, the stateful function's kind of actually a waste of space.
Yeah,
we're being super critical. We're saying, actually, we're probably going to bypass this idea.
Yeah, I mean, I will personally probably see using that, because for my work, like I have to do packages because I code for people. That's the thing. So I don't want to mess up with their environment because I don't know what they have. And I mean, CRAN will allow me to publish something with a super assignment. And now that I think of it, it's actually a good idea, because you want to respect your user's environment. So you want to override things here and there. But yeah, that's my take on the super assignment thing.
It's really insightful.
You could use a sign though, right? And just be explicit about using the parent environment.
Yeah. But then what if the parent environment is the global environment?
Well, if it's a function factory, wouldn't the parent environment always be the place where the function was created?
Yeah.
Yeah. At least I think.
Well, but the very root is usually the global environment, right? So so the function factory has its own function, and when you assign a manufactured function to it, it encaptures that environment, and that holds, for instance, whatever value you've put in there, which allows it to. So, for instance, with the exponent example, it holds the number 2 or the number 3 in there, which we've assigned to the exponent value of the outputted manufactured value, and its root would be the global environment.
Yeah, actually, now that I think about it, if you like used parent environment as the environment in a sign, I think it might actually use, like if you were calling it in global, it would use global. I think you might have to use that Erlang function environment as your assignment spot for like one of those counter functions. Because that will always look to the environment in which the function was created.
Can we create additional environment? We can create empty environments, can't we?
Yeah.
Can we order the environments?
Can you order environments? I think
you can tell it what the parent is, I think.
So if you wanted to do a super assignment, does super assignment go all the way up to the parent, or alternatively, if you created an environment that is one level up from the environment that you're in, that holds the value that you want to maintain the state?
Yeah. It always assigns to the one that's immediately above it.
So you could. So I was just thinking a way that you could bypass it.
I think what it is CRAN probably just has like some kind of regex detector that sees if you have that assignment operator, and they're just like, no. And they just won't let you use it, is probably how they do it.
Stephen, have you used function factories much in your work?
Only in ggplot2, really. I mean, I use metaprogramming more, what I think is metaprogramming, where instead of making a function factory, I will like make a list and change out arguments based on conditions, and then use like exec to call a function. So instead of like using a function to solidify one argument to it and passing out another function and using that, I'll just like vary the function based on conditionals. It's not the same thing. I haven't really used it other than like in scales, as he shows in the graphical function factories section. That's the only time I've really actually used function factories, is like using the scales, or using different things to using functions that will tell you how to label an axis.
Yeah. Personally, I've only ever used it for box-cox transformations before, actually, which I thought was really cool at the time, and then found out that most programs, some other programs just do it automatically by itself. So that was besides the point. But it does seem like a very cool idea. It does seem like something that could be very useful in the long run. I think that perhaps, as mentioned, the examples aren't necessarily, they're a good way of displaying how it's used, but not necessarily a good way of actually saying, well, this is what, you want to use this on a regular basis. And what I've found when I've been looking online for what other people have been doing is essentially all the same examples. There's very few new examples, or very few places where people say, oh, well, we should use this outside of things like graphs or box-cox transformations. And the maximum likelihood is probably the most advanced example I saw online, which is a bit sad, really.
Yeah, I think it might be because there's easier ways to have similar functionality with some of the functions in Erlang. It's like you can replicate some of the things that function factories do in other ways, and I think that's might be why it doesn't get used so much. And like R6, like Roberta was saying.
Function factories in other languages? Because like I know in my graduate department. R is for the faculty is still kind of new, so it's not really like something they're gonna teach unless it was in their language they learned before.
I'm not familiar of this same sort of format in Python, but I also use R more than I use Python. And I have never used this in R before, so my expertise should not be trusted in this situation.
I cannot think of a language in which you will use a function factory, because then I'm used to like the object-oriented programming thing, which is just classes. So you have a class and then you create an object of that class and then you do things on that object, like, and then you have, the cool thing is, you'll see with R6, is that inside the class, it's a list and then you have variables, you have public and private functions, which that's something interesting, because then you say why you want something private. And then that's to replicate some behavior that you want something in your class, but you want users to interact with that. You want something in the background. But no, I've never seen function factories before.
Maybe on functional languages, looking at Haskell, it has it. So I can imagine that in functional programming, you will find those.
Well, in R6 and mirroring object-oriented, I mean, that's like just a more complex version of function factories, isn't it? I mean, it kind of replicates the same idea, is you have a top-level environment, and then you have that is a function, and then inside of that, you have these different like methods that are also functions that operate out of that internal environment, because that internal environment is usually changing based on external input. Like I know R6, the places I've seen it used are like with Selenium, and Selenium's originally a JavaScript thing. It's like a automated web browser engine. And so it has, you make a Selenium like a remote driver object, and that kind of saves the environment of the browser that you've opened. And then as you like give it commands, the actual browser goes and like loads a page and everything loads into it. So the actual environment inside of the remote driver changes as that loads. And then when you call another function, it's going to be based off of that new environment. So that's where it's kind of useful, in that you create like this object, and then it has all these sub functions that modify or interact with that internal environment that's changing. WebSockets as well, where you're like receiving data over the internet that's like updating every 5 seconds or so. Like you initiate the connection with like a function, and then you have functions inside of it that access the data in different ways that's coming in every 5 seconds. So I guess that's another version of a function factors, and both of those originated in JavaScript. So. I think R6 just kind of supersedes this. This is kind of like an intro to what we're going to learn in R6, I imagine.
Do you think that's what the point is then, is to get us used to the idea of these state-based functions?
I think so, yeah, because that's like what R6 is. And like when I first started trying to use R Selenium, which used R6 classes, I was like, what is this? Because it, Roberto was laughing because it's like, what? It just looks totally different, and you use it totally differently than typical R, and it's really confusing if you don't know what you're really doing.
I look forward to that. Did
Yeah,
anyone?
so I think this is like a gentle intro to how it's actually doing what it does. And now like I'm like looking back on that and I'm like, oh, okay. Now I'm starting to see like why they do it that way, basically why it looks that way.
Did anyone get to the questions?
They were pretty basic.
Yeah, it was a pretty basic chapter, wasn't it?
The only one that I struggled, or the one, well, I struggled with a couple of them, but the moment one, the one about like the central moment of the thing, I was like, what is this? I had no idea how to do that one.
Yeah, I had to just look up the formula as well.
Were you able to get it from the formula? Like I was clueless even after looking at the formula.
Yeah, it's just the mean. So like instead of the variance where it's to the second power, you just do it to whatever power you pick.
I think it was it was differentiated or I looked at Wikipedia and it had like d of x, like it was differentiated, and I was like, what? I have no idea what I'm supposed to do there.
Yeah, because the moments come from the derivative of the moment generating function. But there's just like a sample estimator that I think I actually found on Wolfram. Let me find it. Yeah, the Wikipedia was confusing. I just used this definition. So you just take all the deviations from the mean to the rth power and the mean of that.
Yeah, I don't know.
He got very like statistics in that chapter.
Yeah, it was obvious that he's a statistician. He's just like, oh, you just do this. So it's so easy, so simple.
Sounds about right.
I mean, I use R, but I realize that I really lack in my statistical knowledge. I look at those function, like the way equations are written, I'm like, I have no clue how to translate that into R functions. Totally clueless. Unless it's something super straightforward like mean or, you know, subtraction.
I think that's something that I'd quite like to look at next, because you know, you can learn a lot of coding and it's really useful, but there comes a certain point at which you stagnate. Well, your progress is hindered by lack of mathematical understanding, and particularly calculus, which my background in is really poor, because you know, I'm more from a scientific background originally, so my background's kind of mostly frequentist statistics, and then anything that's been like tapped on to the side of that, along with you know, probability, but nothing so complex as, you know, learning and understanding mathematical functions that are useful in a lot of the algorithms that we're expected to apply.
Yeah, exactly. Yeah, that you said it exactly.
Yeah, I've been refreshing my calculus and differential equations, because my advisor recently, she said, well, we have these 3 variables, and it was like moisture index, temperature, and what's it, something else. And she said, we want a function to predict moisture index out of these two, but we don't know the shit, like what function is that. And so she said, you can find something that will suit our data. I was like, okay. So I tried so many things, and I was like, no, like my solution at the end was like, we have to look for a function like by parts, like by ranges, because like with temperature, like you can't pretend, maybe you can find the one function that predicts the values for at different temperatures, but like it was happening that for lower temperatures it wasn't predicting the values of moisture index properly. And she said, oh, but we want a function that's more flat at the bottom, like for lower temperatures. I was like, but yeah, it's easier said than done. And she was like, I don't know what kind of function it is, but you can get it. You can get one. And I was like, yeah, sure. And so that took me a few days of my life. Oh, it's interesting.
Does anybody have a good grasp on how that optimize function works? Like, as you were saying that, I was thinking about that, but I really like, I've tried to use that before and I don't understand it.
If it's the same as optim, it just uses like a Newton algorithm. So it just, you give it an initial point and it moves in the direction of the gradient. But it like guesses, it uses a numerical gradient.
Okay.
Yeah, I usually use optim. I don't know if it's the same. Probably not, but.
So what is it like, if you were to try to describe like graphically what it's doing? Like, is it trying to find a maximum in a distribution? No.
So you give it a function and yeah, it just finds this one, yeah, it just finds what the minimum or the maximum, whatever you tell it.
Okay. So it kind of tries to like efficiently guess some values around and then figure out like where the gradient is going and finds like whatever the closest minima or maxima is.
Yeah, it just keeps moving along that gradient until it reaches some stopping criterion. Like the parameters didn't change by, some really small number.
Do you know any way to like work backwards from a distribution to a function so you could like use, well, I guess you wouldn't need to, you just use like the max, right? Like, because if you already have the distribution, you just use the max.
I guess. You mean in maximum likelihood?
Yeah, well, the maximum likelihood is going to be, I guess, if it's a probability distribution, that's going to be the maximum, like the highest point on a distribution, right?
Yeah, so you want to find the value of your parameter, which makes your data most likely. So then you'll find that parameter, which in the book it was the lambda. And then that lambda will define the Poisson distribution that your data most likely came from.
Can you describe like situations in which like that becomes useful? Like what kind of phenomena does that help you to understand?
That's all of frequentist statistics is based on maximum likelihood. But like, like you mean specifically the Poisson or just maximum likelihood in general?
No, I mean like things that happen in the world. Like
I mean,
literally like phenomena.
Everything is an assumption. Every model is an assumption. So what is that quote by Box? Like all models are wrong, but some models are useful.
Yeah. You said frequentist probability?
Yeah. I mean, even linear regression, like the LM function uses maximum likelihood, but that one is available like in closed form. So it doesn't have to do optimize.
Well, does anyone have other thoughts on function factories? Sounds like a solid no.
I think it's an interesting concept. Just like as Stephen said, R6 looks like it supersedes it. It's probably a good introduction. Although, like this whole kind of like working through a list of numbers in order to find, optimal distances or the optimal function is actually a really powerful idea in statistics. We did mention before about the maximum likelihood, but obviously you have lambda functions as well, which is what that was talked about. But you can use those in things like lasso regressions in order to reduce down the number of variables, which is perhaps where it becomes most useful. Is the only thing I can think of off the top of my head, and the only place I think I would use that apart from in Box-Cox transformations. But besides that, doesn't really seem to be massively applicable, but that may be because of R6, or it may be because perhaps we just haven't thought about it enough, or there aren't enough examples out there in the world for us to make more use of them in terms of a mental model.
Yeah. If Box-Cox, at least as I understood it, it's like a normalization transformation, right? Like similar to taking the log or something like that.
Yeah, basically, there are quite a lot of rules around using it. I seem to remember reading something not too long ago that suggested that you probably shouldn't use Box-Cox transformations. I can't remember for the life of me why it is. It's usually, typically speaking, in order to correct normalization, it tends to work out better to use logarithmic transformations instead. I'll need to find it because I actually answered a question on the Slack about why it is that you shouldn't use Box-Cox, which I didn't even know at the time until someone asked the question.
It's interesting. Yeah, I haven't used it outside of like a homework assignment.
Yeah, I feel that way about a lot of the things I learn in statistics. I feel like it gets so technical at times, and they try to teach you the formulas and like how to get through the mathematics of it, that it fails to link up to like the phenomenon in your life or problems you might need to solve that it is applicable for.
That's why Bayesian statistics is way better.
Yeah. Yeah, Bayesian equation and like model stuck with me after statistics. I guess the professor I had said he was very much a Bayesian statistician, and maybe he like biased in that way.
That's so funny because I've gotten yelled at for like by another biologist for saying that before.
For saying you're a Bayesian?
Yeah. But they're probably a little too invested.
Yeah. I mean,
It's not
Bayesian just kind
football.
of is intuitive. Well,
It's
the equation
intuitive,
is not
but there is
intuitive.
also the issue of computational power, isn't there?
Yup.
Yeah, it's slow.
Hmm.
You couldn't even do it until like the 90s, I think.
Mm-hmm. Maybe that's why there's such a like distinction between the way it's taught. Maybe people who learned that, or who learned all the other methods were taught how to do them by hand. So that's what they think is the really important takeaway, versus people who have learned a lot of statistics and are teaching it since the invention of computers emphasize the big message more.
Yeah, that makes sense. That's probably it. Yeah, I feel like that's definitely a thing. Like you can notice how, I mean, just in the R community, like the people who have been using R since like the like golden days of R, like whenever it came out, like years ago, approach problems very differently than people who've picked up R in the last couple years.
I mean, the tidyverse wasn't a thing until sometime in the last 10 years, right?
Yeah.
Yeah. Did you guys, I'm sure you probably heard about the new pipe operator and the lambda functions.
Yeah, does anyone want to talk about that? About the motivation? I read something about it, but retained none of it. Just the motivation for changing the pipe and then how that is useful.
Well, I think it's because like, yeah, go ahead.
I was gonna say, they're not changing the old pipe, it's a whole new pipe.
Isn't it functionally the same? It's just now in base R?
Yeah.
And then it seems like they're phasing out the, what is it? The normal one. What's the package? Magit or something? Yeah.
The McGritter pipe.
Yep.
Yeah, I heard they're actually changing the implementation of the McGritter pipe to virtually mirror the base R pipe. And then now you won't have to have the McGritter dependency. I think it's because when you're doing certain things, there's just like such a strong urge to use a pipe because it makes so much more sense to use it. But if you're doing it in a package, there's like all this added overhead when you're using a pipe. And it also makes it such that like when errors are thrown, they get really convoluted if they happen in a pipe. And that's been like a real pain for a lot of people, I think, over a long period of time. And so finally they decided like we should just implement this in base R. And they finally convinced the base R people to do it. It sounds like. So there's going to be, it's like the actual pipe symbol and then like the greater than symbol. And it's going to be built into base R now. And it's going to work just like the actual McGritter pipe, only faster, apparently.
Oh, yeah. There's like this comment from Tan. I don't know what AST means. He said it primarily rewrites the AST, which is quite different from McGritter's pipe. Oh, something about the tree.
It's an abstract syntax tree from like when we did lobster AST, that like little tree that prints out in the console. So I think the idea is that like the native R pipe that we're gonna get is just like a different way of just like making a function just be parsed as if it's like a nested function and not like an infix. Whereas for McGritter, like you would have like two, I guess, like nested branches where you have like the McGritter thing going on, and then you have like the evaluation of like passing one thing to the other function. So yeah, I think that's a really important distinction, that the native pipe doesn't exist. Like you can't like call it or like assign it a different thing, but it's just like something for the parser to recognize and decide that the thing on the left-hand side is an argument of the thing on the right-hand side, rather than like a function that takes the left-hand side as an argument and then passes it as the first argument of the right-hand side function.
Interesting.
Yeah, which is going to just make it a lot nicer when it shows up in a traceback. Because I don't know if you've ever run into an error and gotten the traceback when you were using a McGritter pipe, but it's really like all these steps of like convoluted stuff from inside of McGritter that you're like, what is all that? And now that's going to be eliminated, and it's just going to look like a nested function. They're also doing the lambda function syntax, which is really nice. I'm glad they're going to have like native lambda, because like we were talking last time, that's super useful. I use those all the time. And now it's going to be built into base R. It reminds me of the JavaScript, where you just have like a parentheses around a variable and then like equals and the greater than sign, and then like an expression, and that is a function. So you don't have to write like, you know, x equals function, parenthesis, you know, variables, expression, brackets. It's just a lot shorter. It's going to be like, I think it's a backslash, and then parentheses, and then your variables, and then an expression. And you can use whatever variable names you want to. It's not, I don't think it's out yet though, right? They're like still working on it.
But I think it's in like the development version, if anyone is risky enough. Let me look.
Yep. That's it. That's the update.
Yeah, there's a plugin for Mac, I don't know, for Windows, that you can have multiple versions of R. And
Yeah, I've seen that before.
you can easily switch. Like, let's say you're in our studio, you just switch from the icon, from the menu bar. I don't remember the name though. Let me see.
Well,
I think
the
it's just called R
options.
switch.
Is it like a keyboard level shortcut or something? Because I know you can do it in the options inside of our studio.
I feel like this would have been really useful to know at any point up to now.
What? The pipe?
No, that you can easily switch between different versions of R just because everything breaks.
I don't know. I'm not even seeing an options tab.
I wonder if, you know, like with Bioconda, you can easily switch between Python versions, and if there's like a bioconda method for switching between R versions.
I mean, I know, like, at least in RStudio, it's like, it's in global options. I think it's the top tab under advanced, and there's like a drop down, and then it'll list all of your available R versions. I go look where it is. I mean, I use the Microsoft MKL, the matrix parallel libraries. So I finally just upgraded to R 4.0 like a couple days ago, because they finally released it for with the parallel speedups. Yeah, so it's actually just general basic, and then you go change, and you can choose the different R versions there. It'll show all the different R versions, however many you have installed.
I don't see that.
Yeah, I don't either.
It's not there for you guys?
Mm-mm.
No, are you on a Mac?
No, I'm on a Windows.
Yeah, I think that's
I'm
the
on
whole point.
Linux.
Oh, really? That's weird that they would just like totally omit that option altogether.
Well, I think
I also-
Roberto was saying there's another way to do it on a Mac, right?
Yeah, I just put it in the chat. I've also never tried that. Tried to use more than one version. Okay. I'm gonna get going now, guys.
Oh,
That's
yeah.
good. Thanks, August. Thanks, everybody.
Thank you.
Yeah, thanks, guys. It was really interesting, particularly the bit about the new pipe operator and Lambda. That's awesome. Really good news.
Yeah, that's exciting. All right, bye, everybody.
Who's due next week?
I am.
Oh, yeah.
It'll be interesting.
All right. See y'all next week.
Bye,
Okay,
guys.
thanks, guys. See you later. Take care.
Bye. Take care.
Bye-bye.